Hello, I'm Laurent Grare, working at the Scripps Institution of Oceanography in San Diego, and I'm presenting a study on instrumented wave gliders for Earth interaction and operation research. This work has been financed through the years by several funding agencies such as the ONR, the NSF, and the NASA, and I have been assisted by my colleague from the Earth interaction lab, Luc Lena, Nick Stadom, Nick Pizzo, and Stephen Deaton. This is the outline of my presentation. I will start by presenting the motivation which led us using wave gliders. Then I will present the principle of operation of a wave glider, the strengths and weakness of this platform, and the suite of instruments we installed on our fleet of wave glider. I will then present some comparison between measurement performed from our wave gliders against state-of-the-art measurement performed from the research platform FLIP during the 2017 Langmuir DRI experiment, when two of our wave gliders were sailing around the research platform FLIP. I will then present a couple of study cases showing the capability of our wave gliders to observe natural phenomena. And finally, I will conclude by presenting the latest development we have been working recently. The scientific motivation in using wave gliders in the field is to better understand the coupling between the atmosphere and the ocean, including the role of Earth interaction processes on the upper ocean and submesoscale dynamics. To tackle this goal, we developed and instrumented this autonomous platform in order to conduct in situ measurement for extended period of time. As most of you know, the wave glider is an autonomous surface vehicle which uses the energy of the waves as a way of propulsion. The platform is made out of two units. The float, shown in the top left picture, sits at the surface, and the glider, or the sub, which is totally submerged, stays at a depth of 6.5 meters for the oldest model, the SV2, and at a depth of 8 meters for the newest wave glider, the SV3. The float and the sub are connected together by a cable called the umbilical. The principle of operation is quite simple. Under the action of the waves, the float and the sub move up and down, and this vertical motion is converted into a horizontal motion by the feed mounted on the sub. The movie at the bottom shows one of our SV2 wave glider riding waves during the LCDRI 2017 experiment, while it was in the proximity of FLIP. Once deployed, the wave glider can be driven remotely by sending command to the vehicle through satellite telecommunication. Here is a list of the strengths and weaknesses of the wave glider. I will start with their strengths. As it is an autonomous platform, once it has been deployed and until it's recovered, it doesn't need the presence of people at sea. It's relatively cheap compared to the cost of a research vessel cruise. Since it uses the energy of the wave, its time at sea is in theory unlimited, which allows performing weeks to months long deployment. Because of its small size, the flow distortion around the float, both in the air and in the water, is quite small compared to a research vessel. And again, because of its small size, it can perform measurement really close to the atmosphere-ocean interface. Unlike moored buoys, as it is a moving platform, it provides spatio-temporal measurement. And finally, since our payload is able to perform real-time processing of the measurement and send back to shore average product, we can understand the environmental condition at sea and adjust the trajectory of the wave glider accordingly, depending on the objective of the mission. Regarding their weaknesses, there are two main ones. First, the control and communication unit of the wave glider and the scientific payload are powered by battery pack, which are charged by solar panel. Therefore, the power available for the instrumentation depends on the size of the battery pack and the balance between the incoming power from the solar panels and the power drained by the CCU and the scientific payload. Therefore, depending on the amount of sunshine, the scientific payload needs to be duty cycled to save power. The second weakness of the wave glider is its speed, which is about 1 knot per hour, depending on the wave condition. In some cases, this low wind speed can be challenging driving the wave glider, especially in regions of strong currents. And finally, the third weakness is operational, as it can be challenging to deploy and especially to recover the wave glider when the weather is not great. I'm going to present now the suite of instruments we installed on our wave gliders. We currently have a fleet of 4 wave gliders, 2 SV2s, the oldest model, and 2 SV3s, the newest model. Since most of the data I will present in this talk were measured from our SV2 model, I will detail the instrumentation for this model. At the end of the talk, I will present the differences between our SV2 and our SV3s. So first I will start with the power. The SV2 are equipped with only a 650 watt battery pack and 2 solar panels providing a combined maximal charge of 86 watt per hour. Let's focus now on the scientific instrumentation. On the atmospheric side, variables are measured by 2 instruments. One is a Vaisala WXT 530 weather station, which measures at 1 meter above the sea surface the wind speed and direction, the atmospheric temperature, pressure and humidity, as well as the rain conditions. The second atmospheric instrument is a GIL R350, which is a 3D sonic anemometer which measures the fluctuation of the wind and temperature, from which the wind turbulence, the momentum flux, and the heat flux can be computed. To measure the position of the wave glider, its speed and its motion, we use the dual antenna V104 GPS from Hemisphere. The data from this instrument are used to derive the wave statistics. In addition to this GPS, our wave gliders are also equipped with an IMU from the XSense company. There is also an additional GMS GPS IMU from Novatel, and we use this sensor mostly to do like the motion compensation of the wind measurement. On the ocean side, we mounted a 11-node thermistor chain on the umbilical between the float and the glider. An additional and optional 10-node T-chain can also be hanged underneath the sub-glider, providing measurement of the water temperature down to about 45 meters. Also, both the float and the sub are equipped with a GPCTD from Seabird, providing measurement of the water temperature and salinity at 30 cm and 6.5 meters below the surface. We also use a Teledyne Workhorse 300 or 600 kHz downward-looking ADCP mounted on the float. It provides a current profile from 4 meters down to about 100 meters with a 2-meter resolution. And finally, we mounted a Nortec Signature 1000 5-beam ADCP on the sub, looking upward toward the surface. It provides current profile from the surface down to about 6 meters deep. I'm presenting now some comparison between variables measured from our wave gliders and measured from the research platform FLIP during the Langmuir GRI 2017. In this slide, the comparison focuses on atmospheric variable. Data from the wave glider are reported in blue and data from FLIP in red. From top to bottom, the following variables are presented. Wind speed and wind direction in the top panel, friction velocity U star in the second panel, atmospheric temperature and humidity in the third panel, and atmospheric pressure in the bottom panel. Note that the data shown were measured at the height of the instrument, 1 meter above the sea surface for the wave glider and about 8 meters above the mean sea level for FLIP. No height correction has been applied to both datasets, which explains the bias between the two measurements, for example, the wind speed or the atmospheric pressure. Taking that into account, without going further into detail, the comparison is pretty good, most variables having a coefficient of determination R squared in the range 0.8 to 0.95. This slide presents a comparison of the wave statistics. The top panel is the significant wave height HS, the middle panel is the wave spectrum for the duration of the experiment, and the bottom panel is an example of the wave spectrum at a given time. Once again, the comparison is pretty good, with, for example, a coefficient of determination of 0.95 for the significant wave height HS. The wave spectrum at the bottom shows that the wave glider is able to resolve a large range of frequencies from about 0.05 Hz up to about 0.8 Hz. In this example, we also see that we are able to capture the transition between the equilibrium range and the saturation range. In this slide, we present a comparison of the water temperature measurement. The comparison is not as good as for atmospheric variable or wave statistics, but remain correct. Note that the measurements from the two platforms are not identical, as the measurements from the wave ladder are performed in a wave-following frame, while the measurements from FLIP were performed in a fixed frame. These different frames of reference can explain some of the discrepancies between the two platforms, especially close to the surface and in the neighborhood of the mixed layer depths. This slide shows a comparison of current profile between measurement from the wave gliders ADCP and measurement from a downward-looking ADCP mounted on the hull of the research vessel Sally Ride during the 2017 RCDRI experiment. This figure shows that the main feature of the current oscillation are properly captured by the wave ladder. It also highlights the importance of the upward-looking ADCP in characterizing the current profile in the first few meters of the water column, which cannot be measured from a research vessel. I'm presenting now the first case study which highlights the capability of the wave ladder to observe and characterize the presence of Langmuir cell. The top panel presents the water fluctuation along a crosswind and cross-wave transect. The water profiles exhibit spatial fluctuation, which are distinctive features of the presence of Langmuir cell. This is confirmed in the bottom panel, which presents the spatial spectra of the water temperature fluctuation close to the surface, measured by the wave glider in red and by the mass system in black. The mass system is a device which maps the sea surface temperature underneath the plane. It was installed during the Langmuir surgery experiment in a plane which was flying nearby the wave glider. This second study case is characteristic of a classic sunny day in Southern California, with low wind in the morning followed by thermic winds in the afternoon. The left picture presents the 10-hour time evolution of the solar radiation, the wind speed, the wave spectrogram, and the water temperature. The top right panel shows the water temperature profile at 4 different times of the day. This figure shows in the morning when the wind is low, the heat of the incoming solar radiation is stored in a very thin layer just underneath the RC interface. As soon as the wind speed increases, short wind wave develops, leading to enhanced mixing through direct mechanisms such as wave breaking and also via indirect mechanisms such as Langmuir cells. The surface heat content is then quickly mixed downward, leading to an increase of the water temperature throughout the oceanic boundary layer. So before concluding, I'm presenting the instrumentation we installed on our newest SV3 wave glider. We have two of them now, and they only conducted their first field campaign last November offshore of San Diego. One of the main differences with the SV2 is the size of the float and the sub. The float is almost 1 meter longer, and the sub is slightly wider, making the SV3 faster and more stable than the SV2. Another improvement is the size of the battery pack, which is now 3000 watt, which is about 4 times bigger than the SV2. There is also an additional solar panel which brings the maximum charge capability to 192 watt per hour. Regarding the scientific instrumentation, there are only some minor modifications. We remove the IMU and we replace the GPS IMU Novatel by a newest model, which is less power hungry. The umbilical being longer, the SV3 are equipped with a 13 node T-chain instead of 11 node T-chain. And also the lower CTD and the T-chain hanging underneath the sub has been replaced by a profiling RBR Concerto CTD, thanks to a winch mounted at the bottom of the sub. This new addition allows performing profile of the water temperature, but also salinity, dissolved oxygen, and fluorescence from 10 meters down to about 150 meters. So to conclude, we showed in this presentation that the wave glider can be equipped with a suite of instrumentation to conduct RC interaction and operation research. Such wave glider provide measurements which are consistent with the state-of-the-art measurement from standard research platforms. They also provide new ways to conduct innovative measurements, especially in the vicinity of the RC interface. We hope that the latest generation of wavegliders will expand our capability to further understand the phenomena driving the dynamics of the operation and some mesoscale processes. Finally, we currently have a manuscript in preparation with additional details, which will hopefully be submitted soon. If you have any question, don't hesitate to contact me directly at lgrare@ucsd.edu. And I am also inviting you to visit our lab website, which contains additional information, pictures, and movie. Thank you.